400 million miles from Earth, a moon smaller than our own is erupting with the fury of 400 active volcanoes. While you've been reading this sentence, Io has spewed enough molten sulfur into space to fill a football stadium. We thought volcanic worlds were rare cosmic accidents. We were catastrophically wrong. Imagine if Earth's most violent volcanic eruptions happen not once per century, but every single day. Not in isolated spots, but across 400 locations simultaneously. Not with familiar rock and ash, but with alien sulfur compounds reaching temperatures that would melt copper. This isn't science fiction. This is Io, Jupiter's innermost large moon, and it represents the most volcanically active object we've discovered in our solar system. For decades, scientists assumed dead worlds were the cosmic norm. Rocky planets and moons, we believed, started hot from formation impacts, then gradually cooled into frozen, crater-pocked spheres like our own moon. Volcanic activity was supposed to be a temporary phase, lasting perhaps a few 100 million years before internal heat engines shut down forever. Mars showed ancient lava flows but went quiet billions of years ago. Venus has volcanoes, but they appear mostly dormant. Earth remains active, but even here, we have perhaps 1,500 volcanoes that might erupt in human timescales. Then Voyager 1 reached Jupiter in 1979, and everything changed. Linda Morabito, a navigation engineer examining routine trajectory photos, noticed something impossible in the background of one image. A strange umbrella-shaped plume rose 300 kilometers above Io's surface. At first, mission scientists thought the camera had malfunctioned. No moon that small should have active volcanoes. When they looked closer, they found not one eruption, but 9 separate volcanic plumes captured in a single photograph. The numbers defied every model of planetary cooling. Io spans 3,643 kilometers, across slightly larger than Earth's moon. But while our moon hasn't erupted in 3 billion years, Io resurfaces its entire crust every million years through volcanic activity. The sulfur compounds blasting from its surface reach velocities of 1 kilometer per second, creating plumes visible from space. Some of these volcanic fountains tower 400 kilometers high, nearly reaching the edge of space if they occurred on Earth. But here is what makes Io's volcanic symphony truly disturbing. The energy source powering this inferno shouldn't exist. Traditional volcanic activity depends on internal radioactive decay heating a planet's core. For small worlds like Io, that heat should have dissipated into space eons ago. The moon should be as geologically dead as our own. Instead, Io pumps more heat into space per square kilometer than any other object in the solar system, including the Sun. Tonight, we're going to discover why Io defies every rule of planetary evolution. We'll explore the invisible gravitational forces that turn this moon into a cosmic forge, examine the alien chemistry of sulfur volcanism, and uncover how Io's torment might be teaching us about volcanic worlds orbiting distant stars. By journey's end, you'll understand why this seemingly small moon has revolutionized our understanding of geological processes throughout the universe. 3 major revelations await us. First, we will discover how Jupiter's other moons participate in a gravitational dance that literally kneads Io's interior like dough, generating more tidal energy than 20,000 nuclear power plants. Second, we'll explore how Io's volcanism creates the most alien landscape in our solar system, a world where sulfur snow falls from yellow skies onto lakes of molten rock. Finally, we'll examine how Io's geological hyperactivity might represent the norm rather than the exception for moons orbiting giant planets, suggesting volcanic worlds could be abundant throughout our galaxy. Before we begin our journey to this hellish moon, consider subscribing and hitting the thumbs up button if you're fascinated by extreme worlds that challenge our understanding of planetary science. And here's a question for the comments. If you could safely visit Io for 1 hour, what single volcanic feature would you most want to witness? The most creative answer gets pinned. The story of Io begins with a puzzle that took scientists 20 years to solve. How can gravitational forces alone generate enough energy to power 400 active volcanoes? The answer lies in a cosmic dance so elegant and destructive that it transforms a small moon into the most geologically violent world we know. Let's discover how invisible forces shape the most alien landscape in our solar system. Now let's begin. Chapter 1. Tidal prison. From the previous revelation that Io defies every rule of planetary cooling, we must ask the fundamental question: what force can generate enough energy to power 400 volcanoes on a world that should be geologically dead? The answer emerges from one of the most elegant and destructive gravitational phenomena in our solar system. To understand Io's volcanic hyperactivity, we need to grasp how tidal forces work on a scale that dwarfs anything experienced on Earth. When you observe ocean tides rising and falling twice daily, you're witnessing the moon's gravitational pull stretching our planet's water. The side of Earth facing the moon experiences slightly stronger gravitational force than the side facing away, creating a gentle bulge. This difference amounts to mere meters of water displacement across thousands of kilometers. Now imagine replacing our moon with Jupiter, a world 300 times more massive than Earth. Imagine bringing that gravitational giant 60 times closer than our moon's orbital distance. The tidal forces wouldn't just raise water levels by meters. They would literally squeeze and stretch solid rock with enough violence to melt it. This is Io's reality every moment of its existence. Jupiter's gravitational field creates tidal bulges in Io's solid crust that rise and fall by up to 100 meters taller than most skyscrapers. But here's where Io's situation becomes uniquely torturous. The moon cannot settle into a stable, tidally locked rotation like our moon has with Earth. Two outer moons, Europa and Ganymede, trap Io in a gravitational resonance that forces its orbit to remain elliptical rather than circular. The resonance works like this. For every 4 times Io orbits Jupiter, Europa completes exactly 2 orbits, and Ganymede completes exactly 1. This mathematical precision, known as a 4-to-2-to-1 resonance, creates a gravitational tug-of-war that prevents Io from achieving orbital stability. Every 42.5 hours, as Io completes 1 revolution around Jupiter, it oscillates between being 420,000 kilometers and 423,000 kilometers from the gas giant's center. That 3,000-kilometer difference might seem small, but it translates to massive variations in tidal stress. As Io swings closer to Jupiter during its elliptical orbit, the planet's gravity stretches the moon's shape like a rubber ball being squeezed from opposite sides. Rock that was stressed in one direction suddenly experiences force from a completely different angle. The entire crust flexes, cracks, and reshapes itself continuously. Dr. Alfred McEwen of the University of Arizona calculated that this tidal flexing generates approximately 100 trillion watts of heat within Io's interior, roughly equivalent to 20,000 nuclear power plants operating simultaneously. To put this energy generation in perspective, consider that Earth's entire geological activity, every earthquake, volcanic eruption, and mountain-building process runs on roughly 44 trillion watts from radioactive decay in our planet's core. Io, with 1/4 Earth's diameter, generates more than twice as much internal heat purely from gravitational stress. No wonder the small moon can maintain 400 active volcanic centers. The heat distribution isn't uniform across Io's interior. Computer models by Robert Pappalardo's team at JPL show that tidal heating concentrates in specific zones where rock layers slide past each other most violently. These regions correspond precisely with Io's most active volcanic areas, particularly around the equatorial zone where tidal bulges reach maximum amplitude. The correlation between predicted tidal stress and observed volcanic activity provides compelling evidence that gravitational forces alone drive Io's geological hyperactivity. But tidal heating creates a feedback loop that amplifies Io's volcanic violence. As internal rock melts and flows, it reduces the moon's ability to maintain structural rigidity. A more flexible interior responds more dramatically to tidal stress, generating additional heat, creating more magma, and further reducing structural strength. This runaway process explains why Io's volcanism has sustained itself for billions of years, rather than gradually declining like volcanic activity on most other worlds. Recent observations from NASA's Juno mission have revealed that Jupiter's gravitational field fluctuates more than scientists previously understood. The gas giant's internal structure, with its complex arrangement of metallic hydrogen layers and possible rocky core, creates gravitational anomalies that add additional stress to Io's orbit. These perturbations ensure that tidal heating never reaches equilibrium. Io remains trapped in a perpetual state of gravitational torment. Consider what you would experience standing on Io's surface during a tidal stress maximum. The ground beneath your feet would literally rise and fall like a slow-motion earthquake lasting hours. Existing volcanic vents would intensify their eruptions while new fissures opened in the flexing crust. The entire landscape would reshape itself as gravitational forces squeeze the moon's interior like a cosmic stress ball. The mathematics of this tidal prison are as elegant as they are destructive. 3 moons locked in gravitational resonance, each pulling on the others with precise timing, creating a perpetual dance that generates enough energy to power one of the most geologically active worlds known. Io's volcanic hyperactivity isn't an accident of formation or a temporary phase of cooling. It is the inevitable result of orbital mechanics played out on a scale that transforms solid rock into molten chaos. This gravitational violence sets the stage for understanding how Io's unique energy source creates the most alien volcanic processes in our solar system. But before we explore those exotic eruptions, we must examine how this perpetual heating shapes a world unlike any other. Chapter 2. Sulfur Hell. Having discovered the gravitational forces that power Io's volcanic engine, we now confront an alien landscape where familiar geological processes create utterly foreign results. This is a world where sulfur replaces water as the dominant surface material, where volcanic eruptions paint the ground in colors that would seem impossible on Earth. When Voyager cameras first captured detailed images of Io's surface in 1979, planetary scientists struggled to interpret what they were seeing. The moon displayed brilliant yellows, oranges, and reds arranged in patterns unlike any terrestrial geology. Early theories suggested sulfur compounds might color the surface, but most researchers assumed familiar silicate rock volcanism lay beneath the colorful coating. They were only half right. The Galileo mission, a closer examination during the 1990s, revealed a volcanic system dominated by sulfur, chemistry to an extent found nowhere else in the solar system. While Earth's volcanoes primarily erupt silicate magmas containing iron and aluminum oxides, Io's volcanic regions show spectral signatures of pure sulfur, sulfur dioxide, and various sulfur compound minerals. Temperatures measured by infrared spectrometers reach 1,800 Kelvin, hot enough to melt silicate rock, but also hot enough to vaporize sulfur into its exotic high-temperature phases. Understanding Io's sulfur volcanism requires grasping how this element behaves under extreme conditions. At Earth's surface temperatures, sulfur exists as yellow crystalline solids. But as you heat sulfur past 385 Kelvin, it melts into a flowing amber liquid. Continue heating to 700 Kelvin, and the sulfur transforms into a deep red viscous fluid as molecular chains reorganize themselves. Push temperatures above 1000 Kelvin, and sulfur becomes a dark brown, almost black liquid with properties unlike any familiar volcanic material. These temperature-dependent color changes explain Io's psychedelic appearance. Fresh sulfur eruptions appear bright yellow where material has cooled rapidly. Longer cooling produces orange and red regions as sulfur molecules arrange themselves into different crystalline structures. Areas of recent high-temperature activity show dark brown and black patches, where sulfur reached its most exotic phases before solidifying. The result is a surface that shifts through the entire spectrum of warm colors as volcanic heat varies across the landscape. But Io's sulfur volcanism creates more than just colorful terrain. Dr. Susan Kiefer's analysis of volcanic plume compositions reveals eruption mechanisms unlike anything observed on Earth. When sulfur-rich magma encounters Io's near-vacuum surface conditions, dissolved sulfur dioxide explosively expands into vapor, driving eruptions with spectacular violence. These gas-driven explosions can accelerate material to velocities exceeding 1 kilometer per second fast enough to reach heights of 400 kilometers above the surface. The most dramatic manifestation of sulfur volcanism appears in Io's volcanic plumes, which create umbrella-shaped clouds visible from spacecraft millions of kilometers away. Unlike Earth's volcanic eruptions, which primarily blast rock fragments and ash into the atmosphere, Io's plumes consist largely of sulfur dioxide gas carrying entrained particles of sulfur and silicate material. As this gas expands in Io's thin atmosphere, it cools rapidly, causing sulfur dioxide to condense into snow-like particles that fall back to the surface in colorful deposits. Patera, Io's most powerful volcanic feature, demonstrates sulfur volcanism on an almost incomprehensible scale. This volcanic depression spans 200 kilometers across, larger than some Earth countries, and contains lava lakes that periodically overturn their entire contents. Infrared observations by the European Southern Observatory show temperature variations across Loki's surface that indicate systematic waves of molten material moving from one end of the caldera to the other like a slow-motion tsunami of liquid rock covering thousands of square kilometers. The chemistry of these lava lakes reveals the complex interplay between silicate and sulfur volcanism. Spectroscopic analysis indicates that while the deepest, hottest zones contain molten silicate rock similar to Earth's basalt, the visible surface layers consist primarily of sulfur compounds, with temperatures ranging from 500 to 800 Kelvin. This suggests that silicate volcanism provides the fundamental heat source, but sulfur chemistry dominates surface expressions of volcanic activity. Recent discoveries by the Large Binocular Telescope Observatory have revealed seasonal variations in Io's volcanic activity that correlate with orbital position changes. As Io's elliptical orbit brings it closer to Jupiter every 42.5 hours, tidal heating intensifies, triggering increased eruptions across multiple volcanic centers simultaneously. These synchronized outbursts create global sulfur dioxide clouds that temporarily thicken Io's atmosphere before condensing back to the surface as colorful volcanic snow. To understand the alien nature of Io's environment, imagine standing near an active volcanic vent during peak eruption. The sky above would glow with an eerie yellow-green tint from sulfur dioxide gas scattering sunlight. Fountains of molten sulfur would arc overhead like liquid amber fireworks, while microscopic sulfur particles would rain down around you like radioactive snowflakes. The ground would shift through colors as your footsteps expose subsurface materials at different oxidation states, stepping on a world that literally changes color beneath your weight. The surface composition mapping by the near-infrared mapping spectrometer reveals that different volcanic regions specialize in different types of sulfur chemistry. High-altitude volcanic vents produce predominantly sulfur dioxide eruptions, while low-lying regions show evidence of complex sulfur polysulfide chemistry. Some areas display signatures of sulfur trioxide, a compound so reactive it would be impossible to preserve in Earth's oxygen-rich environment. This chemical diversity creates microenvironments across Io's surface where different sulfur compounds dominate. Regions rich in sulfur dioxide experience continuous freeze-thaw cycles as the compound sublimates directly from solid to gas in Io's low atmospheric pressure. Areas dominated by elemental sulfur remain more stable but undergo color changes as temperature fluctuations alter crystalline structure. The result is a world in constant chemical flux, where the very composition of the ground shifts with thermal variations. Perhaps most remarkably, Io's sulfur volcanism might represent a geological process that was common during the early solar system but has been largely forgotten on other worlds. Computer models by Geoffrey Moore suggest that sulfur-rich volcanism could have dominated many planetary surfaces before oxygen-rich atmospheres and water altered surface chemistry. It might preserve geological processes that shaped terrestrial planets billions of years ago, offering a window into volcanic conditions that existed when life first emerged on Earth. The implications of Io's sulfur chemistry extend far beyond creating colorful landscapes. This alien volcanism drives atmospheric dynamics, surface evolution, and possibly even the chemical environment necessary for exotic forms of chemistry. Understanding how sulfur compounds behave under extreme volcanic conditions provides crucial insights into planetary processes that might occur on worlds orbiting distant stars. But Io's volcanic violence doesn't just reshape the moon itself, it transforms the entire Jovian system into a dynamic electromagnetic environment where volcanic material becomes trapped in Jupiter's magnetic field, creating one of the most spectacular natural phenomena in the solar system. Chapter 3. Plasma Rivers. From understanding how sulfur chemistry creates Io's alien volcanic landscape, we must now explore how this moon's geological violence reaches far beyond its surface to transform the entire Jupiter system. What happens when volcanic eruptions occur within one of the strongest magnetic fields in the solar system? Accretions and volcanic eruptions occur within one of the strongest magnetic fields in the solar system. Creates abattens when volcanic eruptions, as in the solar system, one of the strongest magnetic fields in the solar system, creates a phenomenon that redefines our understanding of planetary magnetospheres. Every second, Io's volcanoes blast 1 metric ton of material into space. Unlike Earth, where volcanic particles fall back to the surface or disperse into a protective atmosphere, Io's eruptions occur in near-vacuum conditions within Jupiter's immense magnetosphere. This volcanic material doesn't simply drift away, it becomes ionized by solar radiation and trapped in Jupiter's magnetic field lines, forming what planetary scientists call the Io plasma torus. The Io plasma torus represents one of the most dynamic structures in the solar system. Imagine a donut-shaped river of charged particles flowing around Jupiter at Io's orbital distance, glowing with ethereal light as electrons cascade between energy levels. This plasma ring contains primarily sulfur and oxygen ions stripped from Io's volcanic eruptions, moving at velocities approaching 100 kilometers per second as they spiral along magnetic field lines. Dr. Fran Bagano's research at the University of Colorado revealed that this plasma torus contains enough ionized material to equal the mass of several large asteroids, all continuously replenished by Io's volcanic activity. Unlike the thin plasma environments around most planets, the Io torus glows brightly enough to be detected by ground-based telescopes on Earth. Amateur astronomers, with properly equipped instruments, can actually observe Io's volcanic influence as a faint ring of light around Jupiter. The energy dynamics of this system stagger the imagination. As Io orbits through Jupiter's magnetic field at 17 kilometers per second, it cuts through magnetic field lines like a conductor moving through a magnetic generator. This motion induces electrical currents exceeding 5 million amperes, roughly equivalent to the electrical output of several large cities flowing continuously through space. These currents create a direct electrical connection between Io's ionosphere and Jupiter's upper atmosphere, forming what scientists call the Io flux tube. Visual evidence of this electromagnetic connection appeared in images captured by the Hubble Space Telescope, which revealed auroral footprints on Jupiter's surface, directly connected to Io's orbital position. As charged particles spiral down magnetic field lines from the plasma torus, they crash into Jupiter's atmospheric gases, creating brilliant oval-shaped auroral displays that mark Io's location, even when the Moon itself is invisible. These aurora spots are so bright and persistent that they serve as a cosmic lighthouse, allowing astronomers to track Io's position through its electromagnetic signature alone. But the plasma torus doesn't simply glow passively in space. Radio observations by the Cassini spacecraft revealed that this charged particle environment generates some of the most intense radio emissions in the solar system. When plasma waves propagate through the torus, they create radio signals strong enough to be detected by receivers on Earth. These electromagnetic storms, triggered by changes in Io's volcanic activity, can disrupt radio communications across the entire Jupiter system. The formation process of the plasma torus reveals the violent fate of Io's volcanic material. When sulfur dioxide and other compounds blast from volcanic vents, they initially form neutral atoms and molecules in Io's thin atmosphere. Solar ultraviolet radiation and electron bombardment from Jupiter's radiation belts quickly strip electrons from these particles, creating positively charged ions. Jupiter's magnetic field immediately captures these ions, forcing them into spiral trajectories that follow magnetic field lines. As newly created ions begin their journey around Jupiter, they undergo a complex acceleration process that transforms them into one of the most energetic plasma environments known. Magnetic field interactions accelerate sulfur and oxygen ions to energies exceeding 1,000 electron volts, roughly 1,000 times more energetic than particles in Earth's magnetosphere. These high-energy ions create a radiation environment so intense that it would be lethal to unprotected humans within hours of exposure. The distribution of plasma within the torus reveals the global reach of Io's volcanic influence. Dense regions of charged particles correspond to Io's orbital position, but magnetic field dynamics spread volcanic material throughout a toroidal volume millions of kilometers in circumference. Computer simulations by Raymond Walker's team at UCLA show that individual ions from Io's volcanoes can remain trapped in Jupiter's magnetosphere for months, slowly spiraling outward until they either escape the system or crash into other moons. Recent discoveries by the Juno mission have revolutionized understanding of how plasma torus dynamics affect Jupiter itself. High-resolution measurements revealed that electromagnetic energy from Io's plasma interactions heats Jupiter's upper atmosphere far more than previously suspected. The 5 million amperes of current flowing between Io and Jupiter deliver approximately 10 trillion watts of power directly into the planet's atmospheric gases, enough energy to significantly influence global circulation patterns in Jupiter's stratosphere. The temporal variability of the plasma torus provides direct evidence of Io's volcanic cycles affecting the entire Jupiter system. When major volcanic eruptions occur, the plasma torus brightens visibly as increased material input creates higher ion densities. Conversely, during periods of reduced volcanic activity, the torus dims as existing plasma gradually escapes or is absorbed by other moons. This creates a dynamic feedback system where Io's geological processes directly influence electromagnetic conditions across millions of cubic kilometers of space. To grasp the scale of this phenomenon, imagine if Earth's volcanoes could somehow electrify the space around our planet, creating glowing rivers of charged particles visible from other worlds. Every volcanic eruption would send material spiraling around our magnetosphere, generating aurora displays and radio emissions detectable across the solar system. This is Io's reality, a world whose geological violence transforms its planetary environment into an electromagnetic beacon, advertising volcanic activity to the cosmos. The plasma torus also serves as a natural laboratory for studying fundamental plasma physics, under extreme conditions impossible to replicate on Earth. The combination of high particle densities, strong magnetic fields, and continuous material input creates plasma instabilities and wave phenomena that challenge theoretical models. Understanding these processes has implications for predicting space weather around Jupiter and developing technologies for future missions to the outer solar system. Perhaps most remarkably, the Io plasma torus might represent a scaled-down version of processes occurring around other stars with closely orbiting planets. Recent exoplanet discoveries have revealed many systems where large planets orbit extremely close to their stars, potentially creating plasma interactions far more intense than anything in our solar system. Io's electromagnetic environment provides crucial insights into how volcanic worlds might interact with stellar magnetic fields throughout the galaxy. The transformation of volcanic material into charged particle rivers flowing through space represents one of the most spectacular examples of planetary-scale electromagnetic phenomena known. But this plasma environment doesn't exist in isolation. It interacts with Jupiter's other moons in ways that reveal the interconnected nature of gravitational and electromagnetic forces operating throughout the giant planet system. Chapter 4. Orbital Dance. Having explored how Io's volcanoes create electromagnetic rivers flowing through space, we must now examine the gravitational choreography that sustains this geological violence across billions of years. The story of Io's volcanic hyperactivity cannot be told without understanding the precise orbital mechanics that trap this moon in perpetual torment. The 4:2:1 orbital resonance binding Io, Europa, and Ganymede represents one of the most stable and destructive gravitational relationships in the solar system. Every time Ganymede completes one orbit around Jupiter, Europa finishes exactly 2 orbits, and Io completes precisely 4. This mathematical harmony, established billions of years ago through gravitational evolution, creates a system where each moon's gravitational influence reinforces the other's orbital eccentricities. To understand how this resonance amplifies tidal heating in Io, consider what would happen if the 3 moons orbited independently. Gravitational interactions with Jupiter would gradually circularize each orbit, reducing tidal stress and allowing internal heat sources to dissipate. Within a few hundred million years, all 3 worlds would become tidally locked in circular orbits, experiencing minimal internal heating and evolving into geologically dead, ice-covered spheres. Instead, the resonant relationship prevents this stabilization from occurring. Dr. Rosalie Lopes' orbital dynamics calculations show that every time Io approaches the point in its orbit where tidal stress might diminish, gravitational tugs from Europa and Ganymede restore the orbital eccentricity that powers tidal heating. The 3 moons essentially trap each other in a gravitational cage where geological violence becomes inevitable. The precision required to maintain this resonance demonstrates the extraordinary stability of multi-body orbital mechanics. Computer simulations by Konstantin Batygin indicate that the 4:2:1 resonance has persisted for over 4 billion years, surviving countless perturbations from asteroid impacts, Jupiter's continuing gravitational evolution, and interactions with the solar wind. Once established, resonant orbital relationships become virtually impossible to disrupt through normal solar system processes. But this resonance doesn't distribute tidal stress equally among the 3 moons. Io, being closest to Jupiter and experiencing the strongest gravitational gradient, absorbs the vast majority of tidal heating energy. Europa receives enough tidal energy to maintain a subsurface ocean beneath its icy crust, while Ganymede experiences minimal heating despite being the largest moon in the solar system. This hierarchical energy distribution creates three completely different worlds from initially similar starting materials. The orbital mechanics become even more complex when considering how the resonance affects each moon's rotation. While all three moons are tidally locked to Jupiter always, showing the same face toward the planet, the orbital eccentricity forces Io to rock back and forth in its rotational motion, a phenomenon called libration. This rocking motion adds additional stress to Io's already tortured interior, contributing to the localized heating that concentrates volcanic activity in specific regions. Recent precision tracking of Io's orbital position using the Very Large Radio Telescope has revealed subtle variations in the resonance relationship that correlate with changes in volcanic activity. When tidal stress reaches periodic maxima during orbital alignment configurations, Io's largest volcanoes show increased eruption rates within days. This real-time connection between orbital mechanics and geological processes provides direct evidence that gravitational forces drive Io's volcanic cycles. The resonance also creates a feedback mechanism that self-regulates the system's energy output. If tidal heating in Io increased dramatically, the additional internal energy would cause the moon to expand slightly, altering its gravitational influence on Europa and Ganymede. These changes would modify the resonance relationship in ways that tend to reduce tidal stress, creating a natural thermostat that prevents runaway heating from completely destroying the moon. Understanding this gravitational dance reveals why Io's volcanic activity has remained roughly constant for billions of years, rather than gradually declining like geological processes on most other worlds. Traditional planetary cooling models assume that internal heat sources diminish over time as radioactive elements decay and primordial formation energy dissipates. Io's tidal heating, however, is powered by orbital mechanics that remain virtually constant over geological timescales. The mathematical beauty of the resonance relationship extends beyond simple orbital periods to encompass complex angular momentum exchanges between the three moons. As Io loses rotational energy through tidal friction with Jupiter, that energy transfers to Europa and Ganymede through gravitational interactions, causing the outer moons to gradually spiral outward. This energy cascade ensures that the resonance remains stable even as the individual orbits slowly evolve. Observations by the Arecibo Observatory have detected periodic variations in the resonance timing that occur on cycles lasting several Earth years. These fluctuations result from Jupiter's own orbital motion around the Sun, which creates small perturbations in the gravitational environment experienced by the Moon system. During periods when Jupiter reaches its closest approach to the Sun, increased solar gravitational influence slightly modifies tidal forces throughout the Jovian system, causing subtle changes in volcanic activity on Io. The formation history of this resonance provides insights into how gravitational capture can create geologically active worlds throughout the galaxy. Computer models suggest that Io, Europa, and Ganymede did not form in resonance, but gradually migrated into this configuration through a process called resonance capture. As the moon's orbits evolve due to tidal interactions with Jupiter, they pass through the exact frequency relationships that allow resonant locking to occur. This capture process reveals that resonant relationships might be common outcomes of moon system evolution around giant planets. Rather than representing an unlikely coincidence, the Io-Europa-Ganymede resonance could exemplify a natural gravitational phenomenon that creates geologically active worlds wherever large planets host multiple moons. Recent discoveries of exoplanet systems with multiple closely spaced worlds suggest that similar resonances might be widespread throughout the galaxy. The orbital dance also explains why disrupting Io's volcanic activity would require intervention on a planetary scale. Proposals for terraforming Io by reducing its volcanic violence would necessitate breaking the gravitational resonance that powers tidal heating. This could theoretically be accomplished by removing one of the three moons from the system, but such an undertaking would require energy resources beyond current human capabilities and would fundamentally alter the entire Jupiter-Moon system. To visualize the elegance of this gravitational choreography, imagine three dancers moving in perfect synchronization, each step precisely timed to reinforce the movements of the others. As one dancer spins faster, the others adjust their rhythm to maintain the overall pattern. The dance continues indefinitely because each participant's motion stabilizes the entire performance. This is the orbital ballet that transforms Io from a potentially quiet ice world into the most volcanically active object in the solar system. The implications of understanding this orbital resonance extend far beyond explaining Io's geological violence. The same gravitational mechanisms that power volcanic hyperactivity on Io might operate throughout planetary systems where large worlds host multiple moons. Recognizing how orbital dynamics can sustain geological activity for billions of years fundamentally changes our expectations for finding active worlds among the thousands of exoplanets being discovered around distant stars. But the resonance relationship that tortures Io also creates unexpected benefits for the Jupiter system, generating conditions that might support life in the subsurface oceans of Europa and potentially other outer moons. Understanding these connections requires examining how Io's volcanic sacrifice enables habitability elsewhere in the system. Chapter 5. Hidden Oceans. From understanding the orbital mechanics that sustain Io's volcanic torment, we discover an unexpected cosmic irony. The same gravitational forces that create hell on one world simultaneously create conditions for potential life on others. Io's volcanic sacrifice powers a chain of tidal heating that maintains liquid water oceans beneath the ice shells of Europa and possibly Ganymede. The connection between Io's geological violence and Europa's habitability emerges directly from the 4:2:1 orbital resonance that traps all three moons in gravitational synchronization. While Io absorbs the vast majority of tidal energy, Europa receives enough gravitational flexing to prevent its interior ocean from freezing solid. Without Io's presence maintaining the resonance, Europa would gradually settle into a circular orbit. Tidal heating would cease, and its subsurface ocean would become a frozen layer indistinguishable from the moon's icy crust. Dr. Robert Pappalardo's thermal modeling demonstrates that Europa's ocean contains more than twice as much water as all of Earth's oceans combined. This vast body of liquid water, maintained at temperatures between 270 and 280 Kelvin by tidal heating, represents one of the most promising environments for life beyond Earth. The ocean floor likely contains hydrothermal vents, powered by the same tidal forces that create volcanoes on Io, providing energy sources that could sustain chemosynthetic life forms. The evidence for Europa's ocean comes from multiple independent observations that confirm the presence of liquid water beneath an ice shell, averaging 20 to 25 kilometers thick. The Galileo spacecraft's magnetometer detected a magnetic field signature consistent with a conducting fluid, most likely salt water moving within Europa's interior. This magnetic induction provides definitive proof that liquid water exists beneath the surface, since solid ice would not produce the observed electromagnetic effects. Even more compelling evidence emerges from analysis of Europa's surface features, which show clear signs of active ice tectonics driven by tidal flexing. Linear fractures called linea crisscross Europa's surface in patterns that match computer models of tidal stress distribution. These ridges and grooves indicate that Europa's ice shell constantly cracks and reforms as tidal forces flex the entire moon, allowing material from the subsurface ocean to occasionally reach the surface. Recent observations by the Hubble Space Telescope have detected water vapor plumes erupting from Europa's south polar region, providing direct evidence that subsurface water can reach space through cracks in the ice shell. These geysers, reaching heights of 200 kilometers, offer the tantalizing possibility that future missions could sample Europa's ocean chemistry without requiring the complex drilling operations needed to penetrate the ice shell directly. The habitability potential of Europa's ocean extends beyond simply providing liquid water. The same tidal forces that maintain ocean temperatures also drive circulation patterns that could distribute nutrients and energy sources throughout the water volume. Convection driven by tidal heating creates mixing between the ocean floor, where hydrothermal activity might release minerals and organic compounds, and the ice-water interface, where radiolysis from Jupiter's radiation creates oxygen and other reactive chemicals. Ganymede, despite being farther from Jupiter and experiencing weaker tidal forces, also shows evidence of a subsurface ocean maintained by resonance-driven heating. The Galileo mission detected magnetic field variations consistent with a conducting layer beneath Ganymede's surface, suggesting that even this outermost major moon retains liquid water due to its participation in the orbital resonance. If confirmed, Ganymede's ocean would represent the largest body of liquid water in the solar system. The chemistry of these tidally heated oceans might be far more complex than pure water ice would suggest. Spectroscopic analysis of Europa's surface by the Keck Observatory reveals signatures of sulfur compounds, chlorides, and organic materials that could originate from oceanic chemistry. These compounds might be delivered to the ocean through meteorite impacts or produced by radiolysis of dissolved materials, creating a chemical environment rich in the elements necessary for biological processes. Understanding how tidal heating sustains these ocean systems reveals the crucial role that Io's volcanic activity plays in maintaining habitable environments throughout the Jupiter system. Computer simulations by Steve Vance at JPL show that if Io's volcanism ceased, perhaps through orbital perturbation that broke the resonance, Europa's ocean would begin freezing within 10 million years. The entire moon would become a solid ice ball within 100 million years, eliminating one of the solar system's most promising environments for life. This creates a profound dependency where potential life in Europa's ocean relies on continued geological violence on Io, the volcanic hell that makes Io uninhabitable simultaneously maintains the conditions necessary for biology on neighboring worlds. This cosmic trade-off suggests that habitability in moon systems might require a balance between extreme geological activity on some worlds and stable liquid environments on others. The implications extend to understanding habitability around giant planets throughout the galaxy. Recent exoplanet discoveries have revealed numerous super-Earth worlds orbiting within the gravitational influence of gas giants. Many of these systems likely host moon populations that could develop similar resonances, creating networks of tidally heated worlds where volcanic activity on inner moons powers habitable oceans on outer satellites. The longevity of these ocean systems depends entirely on the stability of the orbital resonances that power tidal heating. The 4:2:1 relationship binding Io, Europa, and Ganymede has persisted for over 4 billion years, suggesting that tidally maintained oceans could remain stable for the entire history of planetary systems. This stability timeline encompasses the billions of years potentially necessary for life to emerge and evolve in isolated subsurface environments. Recent studies of extremophile organisms in Earth's deep ocean environments provide encouraging evidence that life could thrive in tidally heated oceans like Europa's. Hydrothermal vent communities that derive energy from chemical processes rather than straight that biology can flourish in environments remarkably similar to those expected on Europa's ocean floor. These ecosystems rely on chemosynthesis chemical reactions that extract energy from dissolved minerals and gases rather than photosynthesis. The discovery of how Io's volcanic sacrifice enables potential habitability elsewhere in the Jupiter system fundamentally changes our understanding of where life might exist in the universe. Rather than focusing solely on planets orbiting within their star's habitable zone, astrobiologists must now consider moon systems around giant planets as equally promising targets for finding extraterrestrial life. To grasp the interconnected nature of this system, Imagine Io as the furnace that powers heat distribution throughout a cosmic house. Its volcanic fires generate the energy that keeps water liquid in distant rooms, creating warm environments suitable for life, even in the cold outer reaches of the solar system. Without the furnace's continuous operation, the entire house would freeze, eliminating the conditions necessary for biology. This realization reveals that habitability often emerges from complex interactions between multiple worlds rather than the isolated properties of single planets. The most promising environments for life might exist in systems where gravitational dynamics create both extreme worlds like Io and stable environments like Europa, linked together through orbital resonances that sustain both geological violence and biological potential. The cosmic irony of Io's situation becomes clear. This small moon's geological torment might be enabling the emergence of life elsewhere in its system, making Io's volcanic hell an essential component of one of the solar system's most promising astrobiological environments. Understanding these connections prepares us to explore how Io's unique properties might be common features of planetary systems throughout the galaxy. Chapter 6: Extreme Geology from Understanding How Io's volcanic violence enables habitability elsewhere in the Jupiter system. We must now confront the sheer extremeness of geological processes occurring on this tortured world. Io represents planetary geology pushed to physical limits that challenge our understanding of how solid materials behave under extraordinary stress. The scale of Io's volcanic activity dwarfs anything experienced on Earth by orders of magnitude. While terrestrial volcanoes typically erupt a few cubic kilometers of material over years or decades, Io's largest eruptions can blast hundreds of cubic kilometers of sulfur and rock into space within hours. The CERT eruption observed by the Galileo spacecraft in 2001 created a lava flow covering 1,900 square kilometers, larger than the entire state of Rhode Island, in just 5 months of activity. Temperature measurements from these eruptions reveal conditions that approach the physical limits of rocky planet geology. Infrared spectroscopy by the Subaru telescope has detected surface temperatures exceeding 2,000 Kelvin during major eruptions, hot enough to melt platinum and significantly hotter than typical basaltic volcanism on Earth. These extreme temperatures indicate that Io's volcanic processes involve not just sulfur chemistry, but also high-temperature, silicate magmas that would glow white-hot to human eyes. The eruption velocities on Io reach speeds that would be impossible in Earth's gravitational environment. Volcanic material blasting from Io's surface achieves velocities approaching 1 kilometer per second, fast enough to reach heights of 400 kilometers above the surface before falling back down. On Earth, similar velocities would carry volcanic material completely out of our atmosphere and into space. Io's lower gravity allows these spectacular volcanic fountains to create visible plumes while still remaining gravitationally bound to the moon. Perhaps most remarkably, Io experiences what planetary scientists term volcanic winter conditions, where erupted material actually cools the moon's surface temperature despite the intense heat sources. When major eruptions blast sulfur dioxide into Io's thin atmosphere, the gas absorbs solar radiation and re-radiates it into space, creating a cooling effect that can drop global surface temperatures by dozens of degrees. This represents a geological feedback mechanism where increased volcanic activity temporarily reduces surface heating. The resurfacing rate on Io defies conventional models of planetary evolution. Computer analysis of high-resolution images by Alfred McEwen's team reveals that Io's entire surface gets buried under new volcanic deposits every million years, roughly 1,000 times faster than resurfacing rates on Earth. This means that no geological features older than a few million years remain visible on Io's surface. The moon essentially erases its own history continuously through volcanic activity. This rapid resurfacing explains why Io shows virtually no impact craters despite billions of years of asteroid and comet bombardment. While every other solid body in the solar system displays scars from cosmic impacts, Io's surface appears pristine because volcanic deposits bury impact craters faster than new ones can form. The Moon exists in a state of perpetual geological renewal where volcanic violence erases evidence of external cosmic events. The mechanical properties of Io's crust under extreme tidal stress create geological phenomena unknown on any other world. Laboratory experiments by Agents demonstrate that rapid heating and cooling cycles can cause sulfur-rich rock to develop mechanical properties, resembling both brittle solids and viscous fluids depending on temperature fluctuations. During tidal stress maxima, sections of Io's crust might temporarily behave like thick liquids, allowing massive volcanic eruptions to occur through mechanisms impossible on more stable worlds. Io's volcanic mountains represent another extreme of geological engineering. Some volcanic constructs rise 8 to 17 kilometers above the surrounding terrain, taller than Earth's highest peaks, despite Io's active surface renewal processes. These mountains form through mechanisms unlike terrestrial mountain building, created by enormous volcanic pressure rather than plate tectonic compression. The fact that such structures can maintain structural integrity while surrounded by constant volcanic activity demonstrates the extraordinary strength of materials forged under Io's extreme conditions. The distribution of volcanic activity across Io's surface reveals patterns that reflect deep interior dynamics operating under tidal stress. Rather than concentrating along linear features like Earth's plate boundaries, Io's volcanoes appear clustered in regions where computer models predict maximum tidal heating. The correlation between theoretical stress calculations and observed volcanic locations provides compelling evidence that interior geology responds directly to orbital mechanics on timescales of days to years. Recent analysis of volcanic composition by the Gemini Observatory has revealed that different regions of Io specialize in different types of extreme volcanism. Equatorial areas dominated by sulfur chemistry produce the most spectacular plumes, but relatively low-volume eruptions. Polar regions show evidence of massive basaltic volcanism that produces enormous lava flows, but fewer dramatic atmospheric displays. This regional specialization suggests that tidal heating creates distinct thermal environments within Io's interior. The temporal variability of Io's extreme geology operates on multiple timescales that range from hours to decades. Individual eruptions can begin and reach peak intensity within hours of initiation, creating surface changes detectable by Earth-based telescopes. Some volcanic centers maintain activity for years or decades, while others appear to cycle between dormancy and hyperactivity on schedules that correlate with orbital mechanics. Understanding Io's extreme geology requires grasping how familiar physical processes behave under conditions that exceed terrestrial experience. When sulfur-rich magma encounters Io's vacuum environment, it doesn't simply flow and cool like earthly lava. Instead, rapid sublimation of dissolved gases creates explosive eruptions that can blast material to escape velocity. The same sulfur compounds that create colorful deposits on Io's surface would be completely unstable under Earth's atmospheric conditions. The energy densities involved in Io's geological processes approach the theoretical limits for rocky planet volcanism. Calculations by Torrance Johnson indicate that some eruption sites release energy equivalent to multiple nuclear weapons detonating continuously for months. This energy release occurs not through human technology, but through gravitational forces operating on planetary scales, demonstrating the immense power available through orbital mechanics. To visualize the extremeness of Io's geology, imagine Earth experiencing simultaneous volcanic eruptions at 400 locations, each more violent than Mount Vesuvius, operating continuously for millions of years. The entire planet's surface would be buried under fresh volcanic deposits every few thousand years, creating a world in constant geological turmoil. This is Io's normal state, a level of geological activity that represents the maximum sustainable volcanic violence for a rocky world. The preservation of Io's extreme geological activity over billions of years reveals that some planetary environments naturally evolve toward maximum energy dissipation rather than stable equilibrium. Unlike Earth, where geological processes tend toward balance between competing forces, Io's orbital situation creates positive feedback loops that sustain maximum possible volcanic activity. This represents a fundamentally different mode of planetary evolution, where gravitational dynamics prevent geological stabilization. The study of Io's extreme geology provides crucial insights for understanding volcanic processes on exoplanets, orbiting close to massive stars or trapped in complex orbital resonances. The physical mechanisms that power Io's hyperactivity could operate on even larger scales around other stars, potentially creating volcanic worlds that make Io seem geologically quiet by comparison. These extreme geological processes set the stage for understanding how Io's volcanic violence influences atmospheric dynamics and space-environment interactions that extend far beyond the Moon itself, creating one of the most complex and dynamic systems in the solar system. Chapter 7. Atmospheric Chaos. From examining the extreme geological processes that remake Io's surface continuously, we now encounter the chaotic atmospheric system that emerges when volcanic violence meets the vacuum of space. Io's atmosphere represents one of the most dynamic and unstable gaseous environments known, collapsing and reforming on timescales that range from hours to seasons. Unlike Earth's stable atmospheric envelope held in place by strong gravity and moderate temperatures, Io's atmosphere exists in a constant state of near collapse. The Moon's weak gravitational field, only 18% of Earth's surface gravity, struggles to retain the massive quantities of sulfur dioxide gas blasted into space by volcanic eruptions. This creates an atmospheric system where volcanic activity directly determines how much gas surrounds the Moon at any given moment. The primary constituent of Io's atmosphere, sulfur dioxide, behaves unlike any atmospheric component found elsewhere in the solar system. At Io's surface temperatures, sulfur dioxide exists at the boundary between solid, liquid, and gaseous phases, causing dramatic atmospheric variations as solar heating and volcanic warmth fluctuate across the landscape. When surface temperatures drop by just a few degrees, sulfur dioxide condenses directly from gas to solid frost, causing local atmospheric density to plummet. During periods of peak volcanic activity, Io's atmosphere can become dense enough to support weather phenomena resembling clouds, precipitation, and even primitive wind systems. Observations by the European Southern Observatory have detected regional atmospheric pressure variations that indicate sulfur dioxide weather fronts moving across volcanic regions as eruption rates change. When major eruptions occur, localized atmospheric pressure can increase by factors of 10 within hours. The most spectacular manifestation of Io's atmospheric chaos appears in the formation and dissipation of volcanic plumes that tower hundreds of kilometers above the surface. These eruptions don't simply blast material into empty space. They interact with existing atmospheric gases to create complex fluid dynamics that shape plume structure and fallout patterns. Computer models by Susan Kiefer reveal that plume behavior depends critically on atmospheric density, with the same volcanic vent producing completely different eruption characteristics as atmospheric conditions change. The interaction between Io's atmosphere and Jupiter's immense magnetosphere creates electromagnetic phenomena that further destabilize the gaseous envelope. Charged particles from Jupiter's radiation belts constantly bombard atmospheric molecules, stripping electrons and ionizing gases that would remain neutral around other worlds. This ionization process removes material from the atmosphere while simultaneously creating the charged particle populations that form the Io plasma torus. Seasonal variations in Io's atmospheric density correlate directly with the Moon's changing distance from the Sun during its orbital motion around Jupiter. As Io moves farther from solar heating during Jupiter's orbital motion, surface temperatures drop enough to cause widespread sulfur dioxide condensation. During these periods, atmospheric density can decrease by factors of 100, essentially causing the atmosphere to collapse and reform as surface conditions change. The atmospheric collapse phenomenon creates one of the most dramatic examples of atmospheric instability known in planetary science. When volcanic activity decreases and solar heating diminishes simultaneously, sulfur dioxide begins condensing onto the surface faster than volcanic eruptions can replace it. Within weeks, regions that previously supported substantial atmospheric pressure can become virtually airless, with atmospheric density dropping to levels barely detectable by spacecraft instruments. Recent radio occultation measurements by the Juno mission have revealed that Io's atmosphere maintains a complex vertical structure despite its overall instability. Different altitudes show varying concentrations of sulfur dioxide, atomic sulfur, and trace amounts of other volcanic gases. The upper atmosphere, constantly bombarded by charged particles from Jupiter's magnetosphere, maintains higher temperatures than would be expected from solar heating alone, creating temperature inversions that trap volcanic gases at specific altitudes. The chemical composition of Io's atmosphere changes dramatically with volcanic activity levels and geographic location. Near active volcanic vents, atmospheric composition includes not only sulfur dioxide but also hydrogen sulfide, sulfur vapor, and trace amounts of silicate dust particles. These localized chemical variations create microclimates where atmospheric chemistry differs substantially within distances of just a few kilometers. Understanding atmospheric chaos on Io requires grasping how volcanic sources and atmospheric sinks operate on different timescales. Volcanic eruptions can inject massive quantities of gas into the atmosphere within hours, but atmospheric loss to space and surface condensation operate continuously. This creates a system where atmospheric density reflects the recent history of volcanic activity rather than long-term equilibrium between sources and losses. The atmospheric dynamics also influence volcanic eruption behavior through feedback mechanisms that couple atmospheric pressure to eruption intensity. When atmospheric density increases, it provides back pressure that affects how volcanic gases expand and accelerate through volcanic vents. This feedback can either enhance or suppress eruption violence depending on the specific gas composition and vent geometry involved. Measurements by the Atacama Large Millimeter Array have detected atmospheric tidal effects where Jupiter's gravitational influence creates atmospheric density waves that propagate around Io's thin atmosphere. These tidal effects occur independently of geological tidal heating, but add additional complexity to an already chaotic atmospheric system. During periods when atmospheric and geological tides align, the combined effects can trigger coordinated eruptions across multiple volcanic sites. The escape rate of atmospheric material from Io provides direct evidence of how volcanic worlds lose mass to space over geological time. Current escape rates indicate that Io loses approximately 1 metric ton of atmospheric material every second, mostly sulfur dioxide and sulfur vapor that eventually become incorporated into Jupiter's magnetosphere. Over billions of years, this atmospheric loss represents a significant fraction of Io's total volcanic output. Comparative atmospheric modeling reveals that Io's atmospheric instability might represent a common characteristic of volcanically active worlds orbiting close to massive planets. The combination of weak gravity, extreme volcanic activity, and strong radiation environments creates conditions where stable atmospheric envelopes cannot develop. This suggests that many exoplanets in similar orbital situations might experience similar atmospheric chaos. The study of atmospheric chaos on Io has revealed previously unknown mechanisms for atmospheric volcanic coupling that occur when geological activity exceeds a world's ability to retain gaseous envelopes. Unlike Mars, which lost its atmosphere gradually over billions of years, Io demonstrates how volcanic worlds can experience rapid, cyclical atmospheric variations that reflect immediate geological conditions rather than long-term atmospheric evolution. To visualize the scale of atmospheric chaos on Io, imagine Earth's atmosphere expanding and contracting by factors of 100 over periods of weeks, with entire regions becoming airless while other areas develop dense, gaseous envelopes. Volcanic eruptions would blast enough material into the atmosphere to change weather patterns within hours, while radiation from space would continuously strip away atmospheric components. This is the reality of atmospheric dynamics on a world where geological violence overwhelms atmospheric stability. The implications of understanding atmospheric chaos extend to predicting conditions on volcanic exoplanets where similar processes might operate on even larger scales. Worlds orbiting close to active stars or trapped in extreme tidal situations could experience atmospheric variations that make Io's chaotic system seem stable by comparison. These atmospheric dynamics prepare us to explore how Io's unique properties might represent a common type of world throughout the galaxy, challenging our assumptions about planetary evolution and the frequency of geologically active environments beyond our solar system. Chapter 8. Cosmic Context. From understanding the chaotic atmospheric dynamics that emerge from Io's volcanic violence, we must now place this extraordinary world within the broader context of planetary formation and evolution throughout the universe. Io's unique properties might not represent a rare cosmic accident, but instead a fundamental type of planetary environment that could be common wherever large planets host complex moon systems. The formation history of the Jupiter system provides crucial insights into how volcanic worlds like Io can emerge from initially similar building materials. Current models suggest that Io, Europa, and Ganymede formed from the same population of ice and rock particles within Jupiter's gravitational influence during the early solar system. The three moons began with roughly similar compositions and sizes, yet evolved into completely different worlds due entirely to their gravitational relationships with Jupiter and each other. This evolutionary divergence demonstrates how orbital mechanics can transform planetary destinies more dramatically than initial composition or formation conditions. While Mars and Venus started with different volatile inventories and atmospheric masses, Io and Europa began virtually identical but diverged into a volcanic hell and a potentially habitable ocean world, respectively. The crucial factor determining their fates was not what they were made of, but where they ended up orbiting within Jupiter's gravitational environment. Recent discoveries of exoplanet systems have revealed that giant planets with complex moon systems might be extraordinarily common throughout the galaxy. The Kepler Space Telescope and subsequent missions have identified thousands of systems containing multiple large planets, many of which likely host moon populations comparable to or exceeding Jupiter's satellite system. If even a small fraction of these systems develop orbital resonances similar to the Io-Europa-Ganymede relationship, volcanic worlds like Io could number in the millions within our galaxy alone. The implications of this abundance extend far beyond simple statistics of planetary types. Volcanic worlds like Io represent natural laboratories where extreme geological processes operate continuously for billions of years. These environments push the boundaries of planetary physics, creating conditions where familiar materials behave in ways impossible to replicate in terrestrial laboratories. Understanding how matter behaves under such extreme conditions provides insights into fundamental physical processes that might operate throughout the universe. Dr. Brad Hansen's population synthesis models of exoplanet systems suggest that tidal heating could be a dominant energy source for geological activity throughout the galaxy. While radioactive decay powers volcanism on worlds like Earth for relatively brief periods, tidal heating can sustain geological activity for the entire lifetime of planetary systems. This means that tidally heated volcanic worlds might remain active long after radiogenically heated planets have cooled into geological dormancy. The frequency of tidal heating also depends on the architecture of planetary systems, which varies dramatically among the thousands of known exoplanet systems. Systems with multiple closely spaced giant planets create gravitational environments where moon capture and resonance formation become highly probable. Recent studies by Sean Raymond indicate that such complex gravitational environments might be the norm rather than the exception in planetary system formation. Io's volcanic hyperactivity also provides crucial calibration for understanding how much energy can be extracted from orbital mechanics without destroying planetary systems entirely. The 100 trillion watts of tidal heating that powers Io's volcanism represents roughly the maximum energy that can be extracted from orbital decay without causing moons to spiral into their parent planets within geologically short timescales. This establishes physical limits for volcanic activity on similar worlds throughout the galaxy. The spectroscopic signatures of volcanic worlds like Io could potentially be detectable around nearby star systems using next-generation space telescopes. Sulfur dioxide atmospheres, volcanic heat signatures, and electromagnetic emissions from plasma interactions might provide observational evidence for Io-like worlds orbiting exoplanets within a few hundred light-years of Earth. The James Webb Space Telescope and future extremely large telescopes could potentially identify volcanic moon systems around nearby giant planets. Understanding Io's role within the Jupiter system also reveals how volcanic worlds might contribute to habitability elsewhere in their planetary systems. The same tidal heating that makes Io uninhabitable powers the subsurface oceans on Europa that might harbor life. This suggests that volcanic worlds and habitable environments might commonly coexist within the same systems, linked together through orbital dynamics that require both extreme and moderate tidal heating to operate simultaneously. The longevity of Io's volcanic activity over billions of years demonstrates that some planetary environments naturally sustain maximum energy dissipation rather than evolving towards stable equilibrium states. This challenges conventional models of planetary evolution that assume worlds generally cool and stabilize over time. Instead, gravitational dynamics can trap certain worlds in perpetual states of maximum geological activity, creating environments that remain violently active for the entire history of their planetary systems. Comparative planetology reveals that Io represents one extreme end of a spectrum of tidal heating that might produce a wide variety of geological environments. Worlds experiencing slightly less tidal stress than Io might maintain moderate volcanic activity similar to Earth's, while those experiencing more extreme tidal forces could become completely molten. This suggests that tidal heating could create a continuum of volcanic world types throughout the galaxy. The electromagnetic environment created by Io's interaction with Jupiter's magnetosphere might also be detectable around other star systems through radio astronomy techniques. The intense electromagnetic emissions generated by volcanic material interacting with planetary magnetic fields could provide signatures of volcanic activity detectable across interstellar distances. Radio observations might eventually identify Io-like worlds through their electromagnetic signatures before direct imaging becomes possible. Recent computational studies of planetary system dynamics indicate that the formation of resonant moon systems like Jupiter's might be nearly inevitable when giant planets form with substantial solid material inventories. The gradual orbital migration that leads to resonance capture appears to be a natural outcome of moon-planet tidal interactions, suggesting that systems producing worlds like Io might form automatically during normal planetary system evolution. To place Io's significance in cosmic context, Consider that this single small moon demonstrates how gravitational forces alone can sustain geological activity that exceeds anything powered by radioactive decay or stellar heating. If volcanic worlds like Io are common products of planetary system formation, they represent a previously unrecognized category of active worlds that could outnumber radiogenically heated planets throughout the galaxy. The study of Io also reveals how extreme environments can persist for billions of years without evolving toward more moderate conditions. Unlike Earth, where geological processes tend to stabilize over time, Io's orbital situation creates positive feedback loops that maintain maximum volcanic activity indefinitely. This demonstrates that nature can create and sustain extreme environments for cosmological timescales, expanding our understanding of what planetary conditions might exist throughout the universe. The cosmic significance of Io extends beyond its role as the solar system's most volcanic world to its function as a natural experiment in extreme planetary physics. The geological processes operating on Io provide insights into how matter behaves under conditions of extreme stress, rapid heating and cooling, and continuous mechanical deformation. Understanding these processes expands our knowledge of planetary physics in ways that apply to understanding geological activity throughout the galaxy. This cosmic context prepares us to examine how Io's unique properties challenge conventional assumptions about planetary evolution and reveal new possibilities for geological activity on worlds orbiting distant stars, fundamentally expanding our concept of what constitutes a geologically active planetary environment. Chapter 9. Planetary Physics from Placing Io within the Cosmic Context of Planetary Formation Throughout the Galaxy. We must now examine how this volcanic world challenges fundamental assumptions about planetary physics and reveals new mechanisms for geological activity that operate beyond the limits of conventional models. Io represents a natural laboratory where extreme conditions test the boundaries of how rocky worlds can behave under gravitational stress. The energy budget of Io's geological system defies traditional models of planetary thermodynamics that assume internal heat sources decline over time through radioactive decay and thermal cooling. While Earth generates roughly 44 trillion watts from radioactive elements in its core, Io produces 100 trillion watts through pure gravitational interaction, demonstrating that orbital mechanics can extract more energy than nuclear processes in planetary interiors. This gravitational energy source operates without fuel consumption or decay, maintaining constant output for billions of years. Understanding the efficiency of tidal heating requires examining how gravitational forces convert orbital energy into heat through mechanical deformation. When Jupiter's gravity stretches Io's interior during orbital eccentricity variations, the repeated stress cycles cause rock to flow plastically, converting mechanical energy into thermal energy through internal friction. Laboratory experiments by Harry Green demonstrate that this process can heat materials far more efficiently than previous models predicted, explaining how relatively small orbital variations can generate enormous thermal outputs. The coupling between Io's interior dynamics and surface volcanism reveals previously unknown mechanisms for energy transport in planetary systems. Unlike Earth, where heat from the core must conduct through thousands of kilometers of solid rock to reach the surface, Io's tidal heating occurs throughout the Moon's interior volume. This distributed heating creates convection patterns that rapidly transport molten material to the surface, enabling volcanic eruption rates that would be impossible through conductive heat transfer alone. Computer simulations by Francis Nimmo show that Io's interior likely maintains a partially molten state throughout much of its volume, a condition unlike any other rocky world in the solar system. While Earth's mantle remains mostly solid despite high temperatures, Io's continuous tidal flexing prevents interior materials from solidifying completely. This creates a geological environment where traditional concepts of solid planetary interiors break down under extreme tidal stress. The mechanical properties of materials under Io's conditions challenge fundamental assumptions about how rocks behave during repeated heating and cooling cycles. Sulfur-rich compounds that dominate Io's surface chemistry exhibit complex rheological properties that change dramatically with temperature, allowing the same material to behave as brittle solid, viscous fluid, or explosive gas depending on immediate thermal conditions. Understanding these property variations requires expanding conventional models of planetary material behavior. Recent analysis of Io's gravitational field by the Juno mission has revealed density variations that indicate complex interior structure responding dynamically to tidal stress. Unlike static rocky worlds where density reflects fixed mineral compositions, Io's interior appears to reorganize continuously as tidal heating redistributes material between solid and molten phases. This dynamic interior structure represents a completely different mode of planetary evolution, where gravitational forces prevent achievement of stable internal arrangements. The electromagnetic effects generated by Io's volcanic activity demonstrate how geological processes can create planetary-scale electrical phenomena. The interaction between volcanic material and Jupiter's magnetic field generates electrical currents exceeding 5 million amperes, more than the total electrical output of many human civilizations. This electrical activity influences atmospheric chemistry, space weather throughout the Jupiter system, and possibly even volcanic eruption timing through electromagnetic feedback effects. Io's atmospheric dynamics reveal how volcanic worlds can maintain gaseous envelopes through entirely different mechanisms than conventional atmospheric retention models predict. Rather than balancing atmospheric escape with gradual outgassing over geological time, Io's atmosphere undergoes rapid collapse and reformation cycles that depend on immediate volcanic activity levels. This demonstrates that volcanic worlds can support dynamic atmospheric systems even when traditional escape models would predict complete atmospheric loss. The heat flow patterns measured across Io's surface show that tidal heating creates geological phenomena operating on multiple length and time scales simultaneously. While individual volcanic eruptions respond to tidal stress changes over periods of hours to days, the overall distribution of volcanic activity reflects long-term orbital evolution spanning millions of years. This multi-scale coupling between orbital mechanics and geological processes reveals how planetary systems can maintain complex behaviors across vastly different temporal scales. Understanding Io's planetary physics requires recognizing that some worlds naturally evolve toward maximum energy dissipation rather than stable equilibrium states. The feedback loops between tidal heating, volcanic activity, and orbital dynamics create a system that self-regulates at maximum sustainable energy output. This demonstrates that planetary evolution can produce steady-state conditions characterized by continuous extreme activity rather than gradual cooling toward dormancy. The spectroscopic properties of Io's volcanic emissions provide direct observational evidence of how matter behaves under extreme temperature and pressure conditions that exceed laboratory capabilities. Sulfur compounds observed in volcanic plumes exist in high-temperature phases that can only be created through the extreme heating and rapid cooling cycles generated by explosive volcanism. These observations expand our understanding of material properties under conditions relevant to planetary formation and evolution throughout the galaxy. Io's geological resurfacing rate demonstrates how volcanic activity can completely erase planetary geological history over relatively short timescales. The million-year resurfacing period means that Io preserves no record of early solar system bombardment, chemical evolution, or gradual cooling that characterizes other rocky worlds. This represents a mode of planetary evolution where geological violence prevents the accumulation of historical information typically preserved in planetary surfaces. The magnetic field interactions between Io and Jupiter reveal how volcanic worlds can influence the electromagnetic environments of entire planetary systems. The electrical currents generated by Io's orbital motion through Jupiter's magnetosphere create aurora displays on Jupiter, visible from Earth-based telescopes. This demonstrates that individual moons can create system-wide electromagnetic phenomena detectable across interplanetary distances. Recent theoretical work by Isamu Matsuyama suggests that tidal heating efficiency depends sensitively on interior viscosity, creating the possibility that volcanic worlds could undergo catastrophic transitions between high and low activity states. If interior temperatures rise enough to significantly reduce rock viscosity, tidal heating efficiency could increase dramatically, potentially leading to complete interior melting. Conversely, cooling events could cause tidal heating to shut down rapidly, transforming volcanic worlds into frozen bodies within geologically short periods. The plasma physics environment created by Io's volcanic activity operates under conditions that exceed anything achievable in terrestrial laboratories. The combination of high particle densities, strong magnetic fields, and continuous material input creates plasma instabilities and electromagnetic phenomena that test theoretical models of charged particle behavior. Understanding these processes has applications for fusion energy research, space weather prediction, and astrophysical phenomena around other stars. To grasp the revolutionary implications of Io's planetary physics, consider that this single world demonstrates how gravitational forces alone can sustain geological activity exceeding anything powered by nuclear processes, maintain dynamic interior structures and reorganize continuously, and create electromagnetic phenomena detectable across planetary system scales. These discoveries fundamentally expand our understanding of what planetary environments are possible under different orbital conditions. The study of Io's extreme planetary physics reveals that conventional models of planetary evolution, developed primarily from studying Earth and Mars, might apply only to worlds in relatively isolated orbital environments. Planets and moons subject to strong tidal forces could follow completely different evolutionary paths that maintain extreme activity for billions of years, creating a previously unrecognized category of dynamic worlds throughout the galaxy. These insights into planetary physics prepare us to explore how Io's unique characteristics might influence the search for geological activity and potentially habitable environments on worlds orbiting distant stars, fundamentally changing our expectations for planetary diversity throughout the universe.